As this wind blows off the outer layers of the star, it leaves the core exposed to space. The core will slowly contract and cool over 500,000 years to form a white dwarf. The contraction halts when the pressure in the white dwarf, the former core of the Sun-like star, is high enough to support its own weight. White dwarfs are incredibly dense, compact objects containing about the mass of the Sun in a ball the size of the Earth. A teaspoon of white dwarf material would weigh more than 15 tons. Fusion in massive giants occurs in layers or shells around the core. Much like the layers of an onion, shells of different elements nest inside each other. Each element produced by the earlier fusion of a lighter element will eventually become hot enough to fuse. This generates still heavier elements, which will ignite, and the process continues. This sequence starts with helium, which fuses into carbon, in a process that lasts for 500,000 years. When enough carbon builds up in the core, it will fuse into oxygen for a period of about 600 years. Eventually, the oxygen will fuse into silicon, but that period only lasts about 6 months. Silicon fusion only lasts for about a day, furiously depositing iron in the core. The star has run out of time. Stars can be roughly divided into 3 types. Low mass, with less than about 4/10 the Sun's mass. Medium mass, from 4/10 to about 8 times the Sun's mass. And high mass stars, with more than 8 times the Sun's mass. The fates of these 3 types are very different from one another. We'll start in the middle, with stars like the Sun. A good illustration of the final stages of a medium mass star can be seen in the predicted end of our Sun. In this case, as helium builds up in the core, it will eventually begin to fuse as hydrogen did before it.
So the core has run out of hydrogen, gravity is acting on it, so it begins to collapse it again, gets hotter and hotter and denser until helium begins to burn. So you can actually bang helium nuclei against helium nuclei and build them up into carbon and nitrogen and oxygen. The outer part of the Sun during that phase is still hydrogen, and it swells up under all this heat. So the Sun grows to a much larger size, and the helium reaction is much hotter and brighter. So the Sun gets big and bright and cool at the surface, and we call it a red giant. That phase lasts for much less time than the main sequence phase did. Pretty soon it runs out of the helium or can't burn it anymore. And then for a star like the Sun, it's over with. So it has this intense, dense core of carbon, nitrogen, and oxygen that it can't burn anymore, and there's not enough mass there to crush it to the next level. So it just sits there. And that little core, by now it's sort of half the mass of the Sun is in this core, but it's only the size of the Earth. And that's going to be what's left when the Sun dies. It's called a white dwarf. The rest of the Sun basically keeps puffing up until it's so far away from this dense core that it begins to flow away altogether. And so the Sun kind of loses the outer half of its gas altogether. There's a beautiful planetary nebula for a little while, and then that gas disperses back off into space, and you're left with this dense carbon core. And that's the way that solar-type stars die.
Oppenheimer's mathematical model for how a neutron star could form starts with a high-mass star exhausting its nuclear fuel, going supernova, and collapsing into a 10-kilometer ball with nearly 3 times the mass of the Sun. A neutron star is an object so dense that a teaspoon of its compressed material would weigh 1 billion tons. As the star shrinks to its final compact size, its rotation would increase proportionately until it spins some 100 times per second. Its initial surface temperature would exceed that of the sun's core and would take an incredibly long time to cool down due to its small surface area. It would also possess an equally powerful magnetic field, trillions of times stronger than the magnetic field of the Earth. The model described an object that astronomers of the early 20th century never expected to observe with the best telescopes of the day, an object only for discussion at conferences and in classrooms. In 1939, Oppenheimer collaborated with several other scientists and eventually submitted a paper on how even denser objects could form. Using quantum mechanics and Einstein's theory of relativity, they refined the calculations of an earlier astronomer who postulated an object whose gravity was so strong that even light could not escape from it. The object, later known as the black hole, would not be indirectly observed until the 1970s. A black hole, also known as a singularity, is a massive object that has collapsed all the way down to a mathematical point, an object with zero radius. The math states that density and gravity become infinite at the center. If even a beam of light gets too close to a black hole, it cannot escape. Astronomer Carl Schwarzschild was the first to model a black hole using Einstein's relativity. He calculated the critical distance one must be from a black hole such that its gravity becomes so strong that neither matter nor light nor any kind of information can escape into the rest of the universe. We now call this distance the Schwarzschild radius. Because light cannot escape from inside the Schwarzschild radius, no information from inside can get out. The edge of this sphere is therefore known as the event horizon, because any events which happen inside it are beyond the horizon for us outside. Once an object falls in and crosses this event horizon, it is lost forever. So how do the massive compact objects form?
Most massive stars that collapse produce neutron stars in their core, and that halts the collapse there. But just as with white dwarfs, there's a limit to how much mass a neutron star can have and still hold itself up. We still have this intensely strong gravity, and the neutrons are all crowded against each other trying to hold the thing up.
It's possible that neutron stars that exist in binary systems can collapse into black holes by stealing material from their companions.
And so as I begin piling stuff on it and it begins shrinking further, it will shrink to a point where it becomes a black hole. And actually nothing can halt its collapse then. So all the matter that was in the core of the star just disappears down the black hole, ends up at the center of it in some form, and the star essentially winks out.
Supermassive stars can collapse into black holes under their own mass and do not need to steal mass from a companion. Nor do they necessarily create the tremendous supernova explosions which accompany the births of neutron stars. After Oppenheimer's work in 1939 on neutron stars and black holes, he led the team that developed the first atomic bomb. The creation of that weapon and those that followed would overshadow his work in astrophysics. But it was the United States and the Soviet Union's efforts to control the bomb that resulted in the discovery of one of astronomy's biggest puzzles.
In the 1960s, the United States and the Soviet Union signed a test ban treaty. They agreed not to test nuclear weapons. So the United States put up a series of satellites to monitor the Earth for nuclear weapons. And the way to do that is to watch for gamma ray bursts, because an exploding hydrogen bomb or atomic bomb produces a burst of gamma rays. The scientists were startled when they detected lots of bursts, but the bursts weren't coming from the Earth, they were coming from space. There were lots of gamma ray bursts occurring in the sky.
Astronomers use the term gamma ray bursters to identify the objects that produce these sudden blasts of radiation, and they are still a source of puzzlement. Detailed observations indicate that they are extremely far away and generate the energy equivalent to 1 billion times the energy produced by the sun. But new methods of observation have provided astronomers with more clues, and the mystery may soon have a solution.